These are the section 1.6 notes for precalculus. And again, please make sure you read the e-text first and then come here and go over some quick notes with me and some examples. Okay, in section 1.6, we're finally getting to talking about transformations of functions, how we move them around in the XY coordinate plane. So I'll be going over these examples, but I quickly want to go over some common functions that everyone should know. First of all, you should certainly know a constant function. If I have y equals a constant, we have a vertical line, okay? What's called the identity function is y equals x, up at a 45-degree angle going through the origin. The absolute value function looks like a v. It's like y equals x on this side, but it's y equals minus x on this side because the absolute value of a negative number is the opposite of what it is. So it looks like a v. The standard quadratic function, y equals x squared, looks like this. The square root function, y equals the square root of x, starts at the origin because we can never take the square root of negative numbers. And it goes like this. And when we talk about the square root function, we're only talking about the positive square root. So this is not plus or minus the square root of x. This is just the plus, right? So the positive square root of x. If it was a negative square root of x, the parabola would be going around like this, and that would not be a function because of the vertical line test. So the function f of x equals square root of x just looks like this. X cubed is the standard cubic function. Comes up and goes through the origin like this. And then the cube root of x looks similar to the square root of x on this side, but you can take the cube root of negative numbers, as you know. So it's reflected about the origin because that is an odd function. So it'll be symmetric about the origin. Notice that f of x equals x squared is the best example of an even function. Its reflection is about the y-axis. Those are the standard functions. From there, we want to build in some transformations. So you should understand vertical shifts. If I add a constant to a function, it shifts it vertically upwards. If I subtract a constant, it shifts it vertically downwards. If I instead look at adding the constant inside the argument of the function, if I add a constant, it shifts it to the left. If I subtract a constant, it shifts it to the right. And then we have vertical and horizontal stretching and shrinking as well. Okay, so now if I put a constant in front of the function and that constant is bigger than 1, it simply stretches vertically that function. Every point on that function is c times the original point. And shrinking is if the constant is between 0 and 1, then it shrinks it by that. So if c were a half, then every point on it would be 1/2 of what it was in the vertical direction originally. All right. Now if I put a constant inside with the argument x, we have horizontal stretching or we have horizontal shrinking with the same concept. Okay. Reflection about the x-axis, y equals minus f of x is y equals f of x reflected about the x-axis. And y equals f of minus x is the same thing as y equals f of x, but reflected about the y-axis. When you're looking to go through an order of transformation, you're trying to figure out how do I transform a function with different steps when it's doing a bunch of different things. Think of it in this order. Think of doing any horizontal shifting first, then think of doing any stretching or shrinking, whether that's vertical or horizontal. Then think about doing reflecting, and then think about doing vertical shifting, okay? So, for example, let's say we want to graph the function f of x equals 1/2 square root of x minus 2. We start with our common function. We should know what the graph of f of x equals the square root of x looks like, okay? So it looks like this. So what we first want to think about doing is, what does this 1/2 do? It vertically shrinks by a factor of 1/2. For example, this point 4,2, right? 4,2 would shrink it by a factor of 1/2. It would put it at 4,1 instead. Okay? So I would have this guy here. Instead of having 4,2 be on the graph, which is right here, it'd have 4,1 on the graph. So you can think about it, it shifts it down, it vertically shrinks it by a factor of 1/2 first. Then this minus 2 shifts the entire thing down the y-axis a length of 2 units. So that 0.41 I was giving you an example of being right here, that would be shifted down 2 units down to here. So we vertically shrunk by a factor of a half, and then we shifted down the y-axis by 2 units. All right, let's say we want to graph f of x equals minus the absolute value of x minus 4. So we start with what we understand as a very common function, f of x equals square root of x. We should know, again, that looks like a v. Okay, so what would the minus square root of x do first? That would reflect it about the x-axis. So it would flip this v over so it would be downward facing. Okay, then the minus 4 says shift that down the y-axis 4 units. So there's my downward facing v, shifted down the y-axis 4 units. Okay, now let's graph f of x equals minus the quantity x plus 1 cubed minus 4. So working away from the common function of f of x equals x cubed, which we need to know looks like this, work away from closest to the x away. So this x plus 1, we're adding a plus 1 inside with the argument. So when you do that, it shifts the entire axis 1 unit to the left, right? Adding a positive constant shifts left. Okay, then the negative sign in front of that would reflect it about the x-axis. So this would get reflected. This guy going up would now come down. This guy going down would now come up. Okay, so we see it reflected. Okay, shifted 1 unit to the left. Then we shift down. This minus 4 shifts down the y-axis 4. So I'm coming down 4 over 1 and reflected, and here's my cubic function now. All right, lastly, we want to look at the function f of x equals 2 times the quantity x minus 3 squared plus 1. So we start with f of x equals x squared. We should know, have a good feel for what that looks like. The minus 3, we're subtracting 3, would shift this guy 3 units to the right. The 2 in front of it would stretch it vertically by a factor of 2. Every point would be 2 times where it originally was. And then the plus 1 would say shift the whole thing up the y-axis 1 unit. So there we are.